Good morning. I'm Steve Overberry from representing Friends of ORNL, and it's my privilege today to introduce our speaker, Stephen Jesse. Stephen is a distinguished scientist and head of the Nanomaterials Characterizations section at the Center for Nanophase Material Sciences, CNMS, at ORNL. Stephen got his MS and BS degrees in mechanical engineering and then a PhD degree in material science from the University of Tennessee at Knoxville. He started his interactions with ORNL already as an undergraduate. He conducted research already as an undergraduate and conducted his graduate school research at UT, jointly at UT and at ORNL. After his graduate work, he started at ORNL as a postdoctoral researcher at CNMS, working with Dave Gahagan on lasers and nanotubes, and eventually was converted to staff. Subsequently, his research focused on atomic force microscopy in collaboration with John Winkelkin, Art Badorf, and the late Ward Plummer. Stephen has received R&D 100 awards from ORNL, UT Battelle, the American Ceramic Society, Microscopy Today, and Materials Research Society. Has 14 patents, and is the author of more than 300 articles in refereed scientific journals. I knew of Stephen's work when I was at CNMS before I retired in 2016. And as someone who's had experience trying to work with scanning tunneling microscopy, doing experiments on that, my impression is that his skills and accomplishments with scan probe techniques are nothing short of magical. You will hear some about this today, I think. The title of his talk is Building Materials and Devices with Atomic Precision, Perils and Promise. Thank you, Steve.
Well, thank you so much for the introduction and the opportunity to speak with you guys today. Does it sound good? It's loud enough? All right, awesome. So you heard some of the introduction. I'll give a slightly different angle on it about me. So yeah, I grew up in Middle Tennessee in Hendersonville, right about under the I-65 sign. And, you know, the guitar's there because a lot of country music, and I grew up with a bunch of kids of country music stars. Taylor Swift went to my high school. So, you know, two famous people now from HHS. And, you know, she was a bit later than me, but my sister sent me this picture recently, so I need to share it. While she was making country music, that's what I was doing. That was my chemistry lab. That was me working on the Commodore VIC-20, which predated the Commodore 64, and it was 20 because it had 20 kilobytes of memory. And if your parents bought you that instead of the Atari, then you had to write your own code to play games. So that's where I kind of learned all about science, fell in love with science, knew that's what I wanted to do. It wasn't always that clean. It would typically look like that, where, you know, this wouldn't pass the muster of you know, Oak Ridge safety right now. There's a soldering iron next to some ammonia, maybe some flammables over there. And there was a microscope there too. So, you know, this was kind of where I spent, you know, hours and hours kind of doodling and messing around. And so, yeah, I went up the road to UT, did engineering and material science, and luckily there's a nice lab here where I could continue to do this kind of stuff on a much bigger scale, right? So I was really appreciative that it's there, and so grateful because, you know, it allowed me to kind of stick around and do exactly what I love. And I got to do all kinds of stuff, and you know, throughout the years, they kind of added up, and eventually I found microscopy because I was working with nanoscience, and it was kind of the marriage of everything I like. Because I could tinker, I could do my engineering and modify these microscopes and make them do things that the manufacturers never intended them to do. And then, you know, and I was working in nanoscience, so a lot of these things were operating at the atomic scale. And there we go. And so there are basically three kinds that I'm working on. None of them are the optical kind. So these are typically scanning probes. So you've got an atomic force microscope that's interacting with the surface, STM. We've got atomically sharp tip, kind of measuring current between the tip and the surface. And then electron microscopes that's shooting, really focused electron beams into a sample. And as we kind of progressed in this, we ended up taking lots and lots of data, gigabytes at times, because we were just able to grab so much information at this scale, that we kind of became experts in data analytics, and that adapted to AI. And then most recently, since we're working at this scale, a lot of this directly adapted to working in quantum. And so I'll mostly be talking about this, and I'll give a nice long, maybe too long introduction into quantum information science, because I think it's out there, it's in the news, and there's a lot of maybe misunderstanding what's going on. So hopefully I can give an interpretation of what's kind of happening out there. Okay, so to start with, it's a little laggy. All right. What is information? I won't go to quantum information just yet. What is information at all, right? And what came of it? So there was some theoretical foundation. Obviously, we know Alan Turing, John von Neumann, and their ideas about how you can manipulate simple mathematical expressions and turn them into machinery and have it work. But I think really the fun stuff came with Claude Shannon when he introduced kind of information theory, when he broke information down to its really fundamental limit, right? What's the smallest unit of information you can have? And he came up with a bit, which is just like yes, no, on, off kind of thing, right? And if you start from that perspective, he built up from there, and he was able to basically, the big takeaway that I want to kind of convey is that information is physical. It's always physical. It has an instantiation. You can write thermodynamic equations about information. It interacts with entropy. So the thoughts in your head are, they feel ethereal, but they're actually physical things. And so as a material scientist, as a physicist, and you're talking about information and quantum information, you got to keep that in mind, that it's always a physical entity. And, we see that in all kinds of instantiations here, storage and transmission with lights going on and off, and magnetic fields either up or down. But to actually make it work, the big breakthrough, of course, was silicon, where we could make lots of it, very pure, very crystalline. We had theory to go along with it, with a little bit of dopants. You could, make structures at a very small scale to kind of process information and store it in fields, essentially in electric fields, is kind of how information is stored in all the computers we use now. And on top of having the materials, we had a reliable and scalable manufacturing system, right? So that's why Silicon Valley is Silicon Valley. That's why the information age is the information age that we're living in. It's because in order to do this kind of processing on a scale that matters, you need to have a lot of switches, billions and trillions of switches to do the kind of stuff that we do. And so, basically the whole idea of information is in the digital age is you discretize it to something really small, and then all of your processing calculations and workflows kind of process that serially, right? And that's why we are where we are now. So if we think about what that could mean for quantum, basically we found out 120 years ago roughly that things behave very differently at the very small scale, right? And that eventually became what we call quantum science. And these are the big guys that we all know about, where, Schrodinger came up with an equation that, talks about particle and wave duality. He was informed by lots of other experiments and people fighting over hundreds of years, whether it's particle or whether it's wave. And he's like, yeah, it's both. So he just made some blobby Gaussian and made a differential equation. And he kind of just baked it up, right? He knew there was potential energy and kinetic energy. He put it together, and it worked, and it ended up being one of the most successful predicting equations in the history of equations, right? The Schrodinger equation. And then you've got folks like Niels Bohr who are trying to interpret what this means, and I guess because at the macro scale, the closest thing we've got is probability that looks like it. So they started calling everything probability. Is it really probability? I don't know. But the math sort of works. And so that's the words we use to discuss it. And then you got Feynman, of course, who was brilliant at many, many things and was pretty instrumental in kind of forwarding quantum information sciences itself. And one thing he pointed out is that really all this mystery and strangeness that happens at the quantum scale kind of is all encompassed in this two-slit experiment, right? Where, if you've got a wave coming through and it's split and that can only go through these two ports here, it'll recombine and you'll get an interference pattern because of that. But what's really weird is that this can happen with particles as well, right? So you can send an electron through. Well, this happens in the electron microscope every day. We can split it and it'll interfere with itself going through there. They can do that with protons. They do that with neutrons. It's the whole SNS is based on this kind of thing. They've done it with bigger molecules like buckyballs. I mean, giant molecules that will seemingly go through two slits at the same time and interfere with itself after the fact, which is bizarre, right? It's like playing pool and you kind of hit the cue ball and it sort of spreads out and touches all the balls at once, maybe splashes off the back of the wall smoothly. So it's very bizarre and doesn't match our own understanding of how the world should work. And it gets even weirder too if you think about the fact that if you try to do a measurement to see which hole the particle may have gone through, if you do that, then just kind of acts classically, right? Which is another bizarre thing. And that's the whole Schrodinger cat thing where it's like, is it alive or dead? It isn't one or the other until you measure it, which is a bizarre interpretation. And that became kind of known as the measurement problem. But that kind of reminds me of the country song where it's, I don't have a drinking problem, I've got a drinking solution. So they end up using this problem for a lot of solutions in quantum information science as well. And so, we're thinking about, okay, if you've got this fundamental bit right here, which is two distinct states in classical information, the equivalent is the qubit, right? And it's based off the same idea that I'm not a particle, I'm not a wave, I can be two things at the same time, right? I'm not up, I'm not on, I'm not off, I'm actually a mix of those. And it's not like it's one or the other and I don't know. It's literally, it's a mix of those two states. And, if it's just two, then you can kind of describe it as the surface of the sphere, which is sort of why it's drawn like that. But, so electrons can be both spin up and spin down at the same time. Photon can be polarized, left to right, up or down at the same time, right? And you don't know until you measure it, what it was. And that whole concept is called superposition. And that is one of the fundamental tenets of quantum information science and quantum computing is leveraging this superposition idea. There's another important, one more concept that's important to take away from quantum mechanics that's used in quantum information science. And that comes, one of the best stories I think in science recently is this idea that, Albert Einstein didn't really like quantum. And he helped invent it, but, he didn't like this idea of probability at all. It didn't really fit with his vision of what the universe is like. And he's like, this is crazy. You want to know how crazy it is? And he's fighting at the Solvay conference. There's papers going back and forth. Where he's like, if it's probabilistic and you kind of extend your logic, then you could have two particles come together and entangle and act like one particle. And then you can take them apart and they still act like one particle, which means that I could put the opposite ends of the universe, do something to this, and I'll instantly affect this particle over there. See, isn't that crazy? Quantum mechanics doesn't make any sense. It ends up that his prediction or his attempt to make quantum mechanics sound ridiculous actually was a prediction that worked, right? So this entanglement is a thing, and you can do that in labs all the time. It's a little harder to do than superposition, but you can take two qubits, for instance, entangle them, and you can take two photons and entangle them, and you can spread them apart. If you do something to this one over here, it'll immediately affect this one over there. And the reason it doesn't, violate this faster than light thing is that it took time to get those particles to other, opposite sides of a lab, and so it doesn't ultimately violate the fact that you can't transmit information that fast. But once you get it there, then it's instantaneous because as far as quantum mechanics is concerned, there's no space in between. It's just the same particle. You're just affecting the same system at the same time. And very recently, this was recognized with the Nobel Prize. So these guys did it in the 60s and 80s and sort of demonstrated that you can do this with photons in a lab. And then what Feynman realized, kind of looking at all this, is that he's a fun guy. He played bongo drums and all kinds of stuff. But he saw this and really saw an opportunity. It's like, well, if we can encode information this way, what could happen if we encoded in qubits, right? So let's look into that a little bit. So if you got a qubit, Again, two states at the same time, both 1 and 0. And I'm going to take their little Schrodinger cat, instead of killing it and having it alive, I'm going to make it awake and asleep. I think it's a little friendlier. And this is sort of what this representation is of a single qubit. Now you can add another qubit to it, and what you end up is 4 states altogether, because I'm just going to say that the other state is the difference between happy and sad. So you could be any one of these combinations. So there's 4 states that can exist at the same time because I put 2 qubits together. And if you extend that a little further, it could be awake, asleep, happy, sad, or purring and not purring. Then with 3 qubits, you get 8 states that can exist simultaneously at the same time. And you'll see this exponential increase, right? Every time you add another qubit, you actually double the amount of states you can be in, right? And that's really the secret behind why quantum computing might have the potential that they think it has, because the number of states goes as 2 to the n. And so if you got something like 60 perfect qubits, then you can have 2 to the 60, which is already exascale, right? So with just 60 of these things, you could match what supercomputer at Oak Ridge can do, that's consuming, the electricity of a single village, and the water of a small town. But it could do those kind of computations just with 60 things instead of trillions and trillions of transistors, which is what it runs on right now. And then we can compare that to digital cat here, right? It's pixelated bit, maybe either 1 or 0. If I combine 2, well, then I can count to 4, right? That's not as impressive. And if you have 2 to the 60, well, I can store a pretty big number. And all the laptops you have right now are 64 bits, so I've already accomplished that. This means you can have a bigger memory. Whereas when you have 60 qubits, you can actually do processing at this kind of scale. And where digital cat might have to make a decision, like Robert Frost, 2 roads diversion of wood, and I took the one less traveled by. Digital cat's like, I'll just take all the roads at the same time. Even better, I am all the roads, right? And when I'm ready, my wave function will collapse on the optimal road. And that's really what the secret is. And that's what people are trying to go for with this. And so that might open the potential to solve a whole new class of problems. And some of those, I'll go through a few here. A lot of them have to do with optimization, right? Which is something that's kind of hard and tedious to do in classical computing. So traveling salesman is kind of the classic one where, what's the best, if I know I'm a salesman, I need to go to all these different cities, what's the best path I can do to hit all of them and, cost the least and take the least amount of time? If you're digital cat, you're just going to just write a program and do every route. And then when you're all done, you figure out which one was the best one, right? There's not really any faster way to do it. Travel with your quantum cat, I'll just simultaneously be all routes at the same time. And when I do the measurement, I'll just collapse on the optimal one, right? It just sort of happens. You might have to run it a few times to make sure the statistics are right, but that's really what the power is. And, notice that every time you add a city, your problem expands exponentially, which is exactly what a quantum computer can handle, right? So that's kind of why it's good at that. Another one, and this kind of goes back to what really Feynman was talking about when he said, why don't we make a computer that acts like a quantum thing? It's that, if you're digital and you're trying to figure out how molecules fold, you might tweak the position of one thing and see if your energy has dropped a little bit, tweak it back. But there's so many things you got to tweak to find out if you collapse to the minimum energy. But this is all governed by quantum mechanics. So if you have a computer where at its heart is a quantum mechanical machine, then it's just simulating, what it's best at simulating. So you can kind of set these systems up in a quantum computer because, folding is governed by quantum mechanics, and so is the computer. And so it's kind of an easy mapping. It's an analog of what's happening in the real world. And then finally, there's prime factorization. And really, we have this to thank for nearly all of the funding that we have right now, because prime factorization is what keeps all of our information safe on the internet, right? So basically, you have a giant number that's made of 2 prime numbers, and you might have the big number, but you don't know the two little ones. 2 prime numbers that multiplied to make it. And if you try to do that with a digital CAD, it's not worth your time or electric bill to try to, factor that out, right? But Professor Shore, I think it was in the 80s, he's an MIT professor. He came up with an algorithm that if you had a good quantum computer, then you can basically do prime factorization pretty easily, right? And so the world would crumble, all information would be free, governments couldn't keep anything secret, military couldn't. So, people took notice when that algorithm came out and said, well, we don't want to be the second one to get this right. We need to be the first one to get this right. So that sort of started why, this has become really a big interest now. And then, and I don't have time to go into much of this, but, kind of the antidote for some of that is that quantum can allow you to have secure communication. So again, if you have got entangled qubits and you send information that way, if you have one and someone tries to read it along the way, that means that you will know immediately that happened, right? Because it can only give its information out once. And so if something gets read. And so you can be like, oh, I'm not, something happened. This isn't a secure channel anymore. And so with things like entanglement, you can, have secure communication, or at least know if a signal has been intercepted. And then there's the whole realm of quantum sensing, which is probably the first place that a lot of the applications are going to come out. One, it's useful because quantum things are really sensitive. It's a problem, but you can also use that. But you can also manipulate uncertainty. So you have this velocity versus position uncertainty. Sometimes you can squish uncertainty into one branch, and so you can have, for instance, if you don't know velocity very well, then you can know the position much better. And so you can kind of squeeze that around and use that for better measurements. And then if you got entangled sensors that are sort of spread out, it's kind of one sensor and it's, the way it behaves, but it's spread out. And so you can kind of cancel all uncorrelated noise, which really helps you go below what's possible in the classic sense. So with all that, you might ask, well, why hasn't the world crumbled? I've heard there's quantum computers. Why is Shore's algorithm not being operated right now? And found this little funny meme thing where it's like, okay, Shore's algorithm in theory is this big, strong dog will destroy the world with RSA encryption. But in real life, it's something like this, where it's like, it's maybe 15, maybe 3 times 5. I don't know. I'm 80% sure. And that's really what the computers are kind of doing now. And why is that? Why is it so bad right now? And it's the fact that they need to be perfect qubits, right? Because that is the big issue right now, is that, you have a quantum state, or in theory, you could have a quantum state, many of them entangled, but actually keeping it and holding it long enough to actually do something is a problem. And so that's really the big challenge. And this is kind of the, analogy I have for it. It's like, well, the story I've told you so far is kind of this Norman Rockwell. I'm building a little sandcastle on a beach on a sunny day. In reality, making a qubit be a qubit is more like trying to build a sandcastle in a hurricane, right? But it's even worse than that because, I said you need 60, so you got to build 60 sandcastles before the wave crashes and destroys everything. And then you might be asking, well, what is that destruction? It's actually temperature in many cases. It's many things can do it. But it's almost like if you try to do anything at an elevated temperature, it's almost like trying to build a sandcastle underwater where it just smushes into nothing before you even begin. So you're not going to get anywhere. So that's kind of at the core of the challenge as scientists and engineers to do this. One solution is, and this is the main solution right now, is to just get really cold. So they're pretty close to Kelvin zero in a lot of these machines in order to do this. They've got little gizmos like this where you've got microwave resonators. So there's kind of like a microwave photon going back and forth, and that's your little quantum unit that you can play with. But all that has to be submerged down in these cryostats, and you got to send all these microwave signals back and forth. So that's why they're kind of stuck at 15 roughly qubits, which don't work very well at all. On top of it, when you make it out of something like this, which leverages what we have in terms of semiconductor industry to make something this small, but these aren't identical, right? And if they're slightly different, then that means they'll go out of phase quicker, and so you can't achieve that kind of identical nature, which you need to really do quantum computing on a real scale. And so, the challenges are, I'll just spell it out here, is that we need to have a stable entity that can exist in a superposition of states, first of all, right? So what is that? It has to be physical, we know that, but what, out of many quantum things in the world, what could it be? We know that we don't just need one, we need to have more than one, and they need to be close enough to entangle, and we need to control that entanglement. So that's an added challenge. Another one is that we need to perform operations on it. So say you got these things, and the operations are kind of, they're kind of funny in that sense. With normal classical computing, you just have a logic like and or something like that with two bits. Here it's like, I don't know what you are, but I want you to rotate 90 degrees. And then you can do those operations for a while. There's people working on beautiful algorithms. When the computer is finally built, they'll have some beautiful algorithms to run on them where they run that and they can solve problems that way. But you need to be able to do that, so you got to connect to all of these in order to do those kinds of operations. And then finally, there's transduction, right? Where, maybe I'm working in electron spin, but I need to communicate it out. So I need to somehow get that spin communicated to photon polarization, but I can't know what it is in the meantime, right? To really get quantum communication working, it has to communicate directly through those. And so how do you get those transformations to happen is a really big challenge. So yeah, it needs stability, long coherence, connections, and multifunctionality. And then I know a nice professor, kind of curmudgeonly, but he's been in the business for quite a while. And this was his quote. So every proposed qubit platform so far needs at least 2 miracles to succeed. Digital communication was the same way. Just silicon ended up solving a lot of those miracles for us. And he also said this, which I thought was good, is that a lousy qubit can be a good crapometer, which kind of speaks to why it might be good for sensing to start with. But, sort of this information goal here for quantum is we need to be able to encode, transduce, and process and transmit information. And we need to be able to do this in a physical form and, have superposition and entanglement at the same time. So what are the kind of platforms that are out there right now where we could potentially do this? It's hard to drink with this thing. All right, so this is sort of my quick review of kind of think about what's out there in terms of physical things that people can do. I'm calling this extrinsically quantum because these are things that we build. They're not inherently quantum by themselves, but they leverage a lot of what nanoscience has done so far in terms of making little resonators that support quantum computation. And some of them are mechanical, some of them are electrical. We can build them, but they're not identical, and that becomes a problem. And then when I think about intrinsic ones, these are things that, in and of themselves are automatically quantum just on their own, right? We got photons. It's kind of how we learned about quantum even was a thing, right? So they naturally exist. They exist at room temperature, which is wonderful. And the only problem is it's difficult to couple and it's difficult to manipulate. So the thing that makes them great for being stable means that it's also hard to interact with them. So there's a lot of materials problems going with, making nonlinear optical materials where you can manipulate photons. Quasi-particles is completely bonkers kind of thing where it's not one of these guys here, but you can set up material in a certain way, and essentially if you make an edge with the right kind of material, that edge has to have a certain quasi-particle that you can operate on. And so the stability actually comes from the fact that you can cut things a certain way, and then you can have those interact and braid. And this is, what I maybe 2 months ago when I presented this, it was like, is it even possible? And actually Oak Ridge is doing quite a bit of work in this area. And then, 3 weeks ago, Microsoft unveiled that they were able to do this to some extent, doing these topological quantum systems and actually do some computation that way. So, the world is progressing. In terms of atoms, there's kind of 2 big categories. One is to kind of take your atom and levitate it in a vacuum. And there are systems for doing that where they can shuttle atoms on top of a chip. And I don't know if you can see them back there, but they're little bright dots that they've got levitating in space, and they can shine out lasers on them and flip their spins or whatever they want to do and manipulate it. So you can set up a state and sort of let it run out and do its thing. Bose-Einstein condensates sort of fall in that same category. But another place where atoms kind of tend to show up is in everything else, right? I mean, in stuff. So the concept is, well, dopants and defects kind of act like atoms on themselves, and sometimes people even call them artificial atoms. So, if you've got perfectly pristine material, you put a different kind of atom in there, it might have an electron that spins around it, and it sees it as kind of its own little atom. And so, some of these little defects can actually act like atoms, but they're stuck in material that you don't have to worry about levitating them or anything like that. So the question is, are there some good candidates for doing that in the real world? And that's sort of the area that I'm working on right now. So can we devise means to adapt the instruments that we use to see atoms at the nanoscale and act upon these materials to build useful structures, right? And, can we make targeted quantum defect creation possible, right? So that's the big kind of question that I really want to go after. And, can we make these kind of structures on demand and put them where we want to put them so they can do their quantum behavior in a controlled space? All right. Yeah. And then just a little comment about defects, because I gave a talk recently into a conference that was all about defects, and I was like, I don't like the word defects. I mean, this is really what I'm trying to do. Defect has a kind of a negative connotation. And so the concept is, if you've got this perfect lattice of atoms and someone puts a hole in it, you're like, oh, that's a defect, that's terrible. But, if you go back to Latin, it's failed to do something, lose strength, blah, 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 terrible. But, someone might find some use in that, right? It becomes a portal. And it's funny because the AI generator that did that actually put the cat in there. So obviously Schrodinger's cat was meant to be in that little hole. And then if you engineer it, you can actually make it into something that's useful. So, you might call it, some people might call it a defect, some people call it the actual thing that you want. And this is kind of an example of it. And then there's another kind of word that kind of has the same derivative in it, perfect. So the question is, can we come up with the perfect defect for doing quantum? And how would you do that, right? Because if these are little atoms and you got to knock them out, almost everything you have is going to be a wrecking ball. So how can you use a wrecking ball to actually make what you want in a controlled manner? And we have some tools that might pave the way for doing that. And that is the scanning tunneling microscope and the scanning transmission electron microscope. These are both kinds of microscopes that allow you to look at atoms at their actual scale and in some cases manipulate them. So a little picture of an STM where essentially the concept is you got a really sharp tip and you can send electrons back and forth across that. That's a little bit of the history. And so basically, you got a tip that you can control, get it really close to the point where you can have tunneling, which is a purely quantum mechanical process, right? So all it means is that I've got electrons over here. I've got this barrier that I shouldn't be able to go through, but quantum mechanics says that, there's actually a probability that that electron will show up on the other side of that barrier, right? And that's just the nature of being smoothed out and spread out over space. And then you can actually measure that current. So you can use that to get the tip really close. You measure the current. And if you're close enough, then okay, I'm really close because I have this current. And you can then scan across the surface and look at all the atoms. So yeah, might be the first example of using a quantum sensor in an instrument. And people have used that to manipulate things in the past. These tend to be atoms that sort of kind of reside on the surface roughly. They don't really do much other than, let you spell things out. But there's plenty of work being done on this to manipulate on surfaces. I think one of the biggest breakthroughs is from Michelle Simmons, where she came up with a way to do lithography where you can take a perfect silicon surface, coat it with something, and then come up with the STM tip and kind of remove some of them. You flood in some phosphorus containing gas, which then bonds, and then you can remove that surface layer and you can incorporate a single atom into a surface. And then she can grow, silicon on top. And so she's put the little defect exactly where she wants it in the lattice. And she's done an amazing work where she's really spelled out what might be possible with this kind of technique of putting phosphorus inside of silicon. So I definitely would recommend, if you're interested in this, to kind of check out what she's doing. It's pretty extensive and enlightening. I know I kind of use it as well as kind of to spell out what I want to do with the electron microscope. But we also do STM-based atomic fab at ORNL. Got a few programs and success stories there. This is mostly led by Anping Li at the CNMS. He's a group leader for the STM group. Here they've done polymerization, where they've been able to write little ribbons of graphene, nanographene ribbons, using just a pulse of electricity on the STM tip in the right environment. They can sort of manipulate atoms around on the surface to make an artificial lattice. So normally you can't get a lattice this big in the real world, but you can sort of set things up. You put the atoms, then it starts to act like special materials that you can't make any other way. Things like Kagome lattices, which have their own special properties. So it's really hard to synthesize something that does this, but if you can kind of position them, then you can start to study those. Atomic chains as well. And what's really, I think, the most important breakthrough, and this is very recent, is putting machine learning and AI into this, where we can set the AI machine, it goes there and it tests how much voltage to put, and it kind of learns how to manipulate atoms around by using the right pulses, the right kind of speeds of moving things, and do it successfully. And so you can actually have machine learning build a lot of these structures, and it's working now. And this has been done within the last year or so, shown successfully. And then, of course, an STM is a great microscope too, right? So you can do all kinds of awesome spectroscopy and then study the material. So you can make them and then study their properties at the same time. And that becomes a really nice closed loop for studying these kind of things, right? Because you can tweak one thing and see how that affects. So you're really working at that atomic scale and be able to interact with these phenomena that you really can't have any access to any other way. So then focusing on the scanning transmission electron microscope. So if you're not familiar with it, it is essentially you have a very highly focused beam. It's focused down to less than an angstrom, so a tenth of a nanometer, less than the atomic spacing of atoms in a material. And you can shoot that beam through, and it transmits through, and then you collect information on the back. And what we're doing is kind of putting a fast computer in the loop where we feedback on the information there and manipulate the beam position and study any transformations that are happening while it's going on, and use that to kind of control transformations at the atomic scale. And so, if you've got one of these microscopes, and Oak Ridge has many, we're really blessed to have as many microscopes as we have that can do this kind of imaging on a routine basis. So this is graphene. It's a 2D material. It's just one single layer of carbon atoms linked together in this hexagonal pattern, sort of like, chicken wire. And it's just suspended in space, right? We have it held at the ends, but it's just one single layer of atoms. And graphene has all kinds of amazing properties, but we can just image it. And these are the atoms that we're just looking at right there. It's quite amazing. So we can see, all of this, and then we can use this to beam to sort of induce damage with atomic precision. And we sort of got on to this thread, might be 10 years ago, maybe a little more now. So Albina Borisovich, she works at Oak Ridge. She was looking at this interface between crystalline strontium titanate and amorphous strontium titanate. And she was kind of scanning across there, doing some measurement. And then she went back and looked at it. I was like, oh, wait, it grew a little bit. That's weird. And it could work even further. So she was actually, in this case, the beam was crystallizing epitaxially the surface here. And so she could extend out the atomic lattice further. And so when we saw that, we said, oh, well, I'm a controls guy. I like to control things. I like to control robots. This isn't much different. What if we come up with a way to do that systematically? So we did this thing where we scan the beam back and forth. We're controlling it. And the whole time it's kind of registering the response in the sensors. And if we're in the amorphous region, we get this sort of flat response. If we're in the crystalline region, it'll kind of have the periodicity of the lattice. And if you take the FFT of that, you'll see that, you get a nice peak there when it turns crystalline. And so that becomes the measurable that says, hey, it's crystalline. And so we can monitor this. We have a set point, We just scan back and forth. When it hits crystalline, we go to the next level, go to the next level, and then we can kind of shape things the way we want to. And you can do, extremely important things like write your institution name in atoms. And it's, literally epitaxial growth. It's a single crystal going through there. You can see the little atoms there, or get on the cover of a journal. All important. But, we showed we could also do it to some extent with silicon. We can move dopants, and it matched nicely with a lot of the models that we could generate as well. So that was the big inspiration that said, okay, this might be possible, right? But then we started looking at two-dimensional materials. Graphene is one example that I talked about earlier. And there's a lot of advantages potentially using 2D materials. The first one is if we're in a microscope and you're looking at a 2D material, then you see all of the atoms, right? If you're looking at 3D, you're always looking at the shadow of whatever material it is. So you don't really see how many atoms there are in the stack. So that's a disadvantage. If it's 2D material, then you know where every atom is. It means you can take a picture, take it to your theory friend and go, hey, what does this mean? And they can directly put that into some, DFT or some other modeling that they can, really understand what's happening. And the other concept is too that there's a lot of potential for using defects in these 2D materials to be qubits as well. And this I'm showing the nitrogen vacancy center in diamond. So this is like the quintessential awesome defect, which acts like a qubit, right? I can't go into too much detail here, but essentially you've got perfect diamond. You remove 2 carbon atoms and you put 1 nitrogen in and leave a vacancy. And it just sets up the band structure perfectly, where you've got a single extra electron that can hop back and forth between different energy bands. And in hopping, there's actually spin selection. So if the electron has a certain spin, it'll go to a certain energy, which means you can read out exactly what that spin was. It also means that, you could shine light of a certain polarization and it'll behave a certain way. So it becomes a nice way to do the transduction, spin selection, spin control, all in one tiny little package. The problem is that it's really hard to get a defect exactly where you want in a 3D material, especially diamond. It's a stubborn material, and it's also kind of expensive, I'm told. Yeah. So, are there alternatives in the 2D space? And can we explore them? And there's other advantages too. We can induce strain, which is important. We can stack them, so we can induce different properties as we stack these 2D materials, and we can twist them. This is a huge area of research right now because you get these Moire lattices where you can get periodicity that's different than the atomic periodicity. But we still need to be able to create in place and test these defects individually. And so we kind of went down this road here, and here we've got a little silicon atom inside a graphene lattice, which I hope you can see there. And Andre, who I hired as a postdoc, tediously went through and found that if you had this silicon atom, you can knock out the carbon next to it, and it would kind of flip positions, and then you can kind of get this atom to move through the lattice. So it's literally inside the lattice, but we're using the beam to kind of guide it through. And it's like, okay, can you get it over there? And it's like, yeah, it's directed, but I wouldn't say it's direct, right? It's kind of randomized a little bit, so it's hard to get it where you want to. But, he's able to make a few structures, and this is silicon and graphene, kind of putting them together. So success, but not really scalable, right? It's a really complicated thing to do, and it's really tedious. So are there better ways? And we came up with this approach where we've got this electron beam over there. We've got a pristine lattice, just one layer of it, and maybe a few absorbed mobile atoms on the surface. We can take this beam and we can scan it around. Again, I'm controlling it with my own electronics, and I'm saying, okay, dwell on this little atom until it knocks out. And then we can stay there and keep looking at it until we see that it's filled with a dopant atom, right? And so with this kind of technique, we can more or less precisely position atoms within, a few atomic spacings of where we wanted to put it in the surface. And we found that it's also pretty general, right? We could use this for quite a few different elements, and it seemed pretty general. Everything we tried pretty much worked. So that was a pretty nice way to go. And we could, kind of control the coordination a little bit to some extent. And this is sort of the method that it's done. So we can image, and then we do this milling thing where we do this little spiral scan, and that's our little drill bit. And what's really kind of neat is that when you do this scan, first of all, you can scan really quick because it's not this, you're not making the magnetic field go to move the beam back around. It's just these smooth sinusoids that, microscope likes. And what's really cool too is that because you do it this way, your dose is really the most at the center. And so you're most likely to get a hole at the center of the thing that you're imaging. So we can do this and image while we're drilling. And so you get a picture that looks something like this, where if we measure the mean intensity as we drill a hole, the hole gets bigger and bigger until boom. We call it, it hit this threshold. We say, okay, that's a hole. And then we just go to a new location and we can start to drill holes in a pattern, right? Yeah, something like this there. And one important aspect of doing work with graphene is that you have to be able to control temperature. We've got special tips for doing that. And the reason is that, everywhere, and now I even do it, you draw pictures of graphene, it looks something like that. In reality, it's pretty junky. It's just one layer of atoms, it's carbon. If you have one more layer of atoms, then half of what you're looking at is junk. But you tend to have many, many layers of junk on top. And so, is it graphene or is it junk that you're looking at? And then, you can zoom in and sometimes you can find these clean regions. And so if you look in literature and you see a picture like that, you can almost guarantee that there's a bunch of junk on the outside. It's a sad truth. And then if you zoom out, you might get this volcano of junk that was attracted to the beam as well. So it's even worse than that. But what we did find is that if we rapidly heat the sample in the microscope, we can get acres, and by acres I mean a square micron of clean material that we can operate on. And it also allows us to control the mobility of these dopant atoms on the surface. And so we thought, okay, we've got our system. Let's do a systematic study. This will be easy and wonderful. We'll just figure out what the relationship is between temperature and what it takes to drill. It ends up that we ran into, these really unexpected kind of results that made us scratch our heads for a little bit. Which, it's kind of why we get up in the morning, is to kind of get surprised like this. So if we're at room temperature, this is an example of some of the junk that forms. We drilled holes. You see it's okay. Increase the temperature, it gets cleaner. But even if we drilled a hole, it sometimes grows back a little bit. And that's possibly because there's carbon on the surface that fills in the holes that we drilled. Around 600 C, we started getting more and more reliable, but still not perfect. And then, we get to 900 C, and first of all, it takes forever to drill a hole. And then we go even hotter, and it's like, we just can't drill a hole, right? It's the weirdest thing, because we expected a higher temperature for the atoms to have more energy, so it just needs less of a kick to actually knock it out of the lattice. That was our anticipated result. That was our hypothesis, right? But it didn't prove out to be true. And if we kind of plot, how long it took to, or how much dose it took to punch a hole at these different temperatures, we see that it just increases rapidly. And this isn't really where it happened. This is just kind of where we gave up. It just took too long to even drill a hole. And so again, it's fast to drill here, but it's filthy, so that's not very good. Here, it's reasonably quick, but sometimes they would fill back in. And then here, we thought, it was wonderfully clean, which is what we wanted, but we couldn't drill a hole, and it was almost impervious. It was, these kinds of doses are just unrealistic for this kind of material. It should just be obliterated, but it's lasting at this higher temperature. What on earth is going on? It ends up that, we looked more closely at what these holes are and how they diffuse around. And me and Yoon did this modeling here. So if you have so this is a vacancy right here. It's a single vacancy of carbon. And just because of random walk, it kind of wanders around inside the suspended lattice and goes around like so, in a fairly random way. And if we kind of look at this, how frequently it jumps from one lattice site to another versus temperature, you see it's pretty dramatic, right? This is a log scale. So at room temperature, it's kind of never. And then at these higher temperatures, it's a million times a second, right? So that's a huge span that we're actually going across here. And so kind of the interpretation is that at this room temperature, it's kind of like, you would think of graphene, it's just this solid, stronger than anything in the world kind of material. And to actually cut it, you need to have something really precise to cut it, right? Something strong. But at this temperature, it's something more like this, where it's more liquidy, right? You can maybe make a hole, but it's going to fill right back in when you're not watching, because that defect is kind of wandering away. It's shooting off at some super high rate. And so it's kind of like this picture here, where it's the T1000, where, you shoot a bullet into it, no matter how big it is, it just kind of fills back in before you can shoot the next bullet. And that's what we were seeing. It was this perfect lattice was actually new atoms kind of filling in that same hole, but they're filling in faster than we could even see it. So that's really what we kind of realized from that. But then the question is, okay, by that logic, how's it possible to drill any holes at all? And we looked more deeply into that and realized that it has to do with the fact that we've got, as we're drilling, we're making more and more of these defects running around in the surface. And as mono vacancies, they move around quickly, but if they ever meet, then they make a stable configuration, which is stable at any temperature, right? And that ended up being the big trick behind why we were seeing what we were seeing. So you get these merged vacancies that can form that. And then you can actually have, if another vacancy sees that, it's actually kind of attracted to the ends just based on the strain states. You can get these chains. And so if you make a little model, this is just like the simplest model you can imagine, just random walk, you're generating these little butterflies flying around. These are vacancies inside of graphene. When they join, they get stuck, and then another one can randomly find it and join to it. And it's kind of a slow, meditative kind of movie. But you can see it kind of one joined right there. And so the next one goes there, then that means that the vacancy, that defect chain got to where the beam is. And so then, only then when you drill the hole, is it actually going to be forming there, because the vacancy doesn't run away. So yeah, it might make some kind of structure like that. And this is just showing different runs where I'm only showing when a defect gets attached. And it's kind of hard to see. Apologize for that. But then we tested that experimentally. And so we modified the experiment a little bit where, we drill for a while and then we do a scan just to image what was happening. And we could see that off in the distance here, we saw exactly this kind of zigzag, it's in the zigzag direction, this defect chain forming. And again, we're drilling here, but the defect chain is forming out there. But at some points it might branch a little bit, and then it might branch again, and then eventually it'll make it all the way to where you're drilling, and that's when we actually form the hole, right? So yeah, kind of a long story to figure out what's happening, but a lot of unexpected steps along the way, which I don't know, it happens every day in nanoscience. It's just like, because nothing really follows your intuition a lot of times, and so finding this kind of stuff is actually kind of fun. And yeah, this is almost exactly what theory would predict we would see. I won't go into that just yet, but the models we made pretty much agreed with our observations. But that's all fine and dandy. Thank you for the science. I thought you were going to make something. So if you need it to be clean, but you can't do it when it's clean, what are your options, right? How can we actually make something, using this principle? And we use one of the most important tools in experimental science, which is, any guesses as to what the solution was? It was luck.
Yeah.
So we looked at a region that was 2 layers of graphene, right? And ends up that everything behaved very nicely there. We went back and looked at the modeling. It ends up that even at really high temperatures, just having that other layer below was enough to slow down that diffusion process. And so we could keep it nice and hot, nice and clean. We could drill, make a defect, and it wouldn't run away before we tried to make another one, right? And so then that on bilayer graphene, everything worked as we wanted to, and we could start to write structures like this and do our most important work there. And it's not perfect yet. I mean, our holes aren't atomic, but these are defects. These are atoms that we've placed there. And those are, individual atoms, and they're within, 1 or 2 lattice spacings of where we intended them to be. So now it's kind of a process of refining that to some extent. Yep. minutes or?
Yeah, 5 minutes.
Okay. I'll run quickly through this, and that's just to say that, our next step and the thing we're working on now is that we need to be able to deliver all kinds of atoms to the surface in order to do this work. And so we kind of need to squunch an entire synthesis lab into this little gap between the pole piece, which is actually really tiny. There's only 4 millimeters total. So we're left about 1 millimeter to do everything that we want to do. And it's in the UHV. No one wants anything else in there. We want to do CVD, pulse laser deposition, heat treatments, all kinds of characterization. Oh, and don't mess up our instrument. They're kind of expensive. And so that's kind of been our challenge recently. And I think we're meeting it. So we're doing things like building our own custom chips where we can heat locally. This is something I did actually over COVID because I couldn't get in the lab. So I made my own little lab again like I did when I was a kid and was smashing Christmas lights and pulling out their filaments. And you can put solder on that and you got a nice perfect evaporator for tin. And so when we finally got back into the lab, we could show that, yeah, this is the filament inside of the microscope. And we actually synthesized 2D tin. We didn't intend to. We were just kind of evaporating it on top of graphene, and it formed its own little 2D structure on there. And theory says it could be useful. I don't know. But, we could also write tin atoms into a surface, into the graphene as well. In terms of doing PLD, we're interfacing a laser. So we're working with a company for doing that, where we kind of bring this element into the UHV environment. We've got an optical fiber that we can move around. Within that tiny space, you got a mirror that's less than 1 millimeter tall, and we can shine laser light on it. And that's kind of, a nice 3D rendering of kind of what we're working on right now. And so that allows us to heat the sample with the laser in situ. We can also, and it does an amazing job of cleaning the graphene. So way better than any other method that we've seen so far. We can also put targets in there, so we can start to do, hit it here and have different materials ablate onto the surface. And another really exciting area that we're working on is incorporating more technology into the sample holders themselves. So we've got a fabulous clean room at the CNMS, which allows us to take regular silicon wafer. We can make these kind of samples that are compatible with the stem. We can put electrodes on them. We can drill tiny holes in them and suspend material across them and work, on these 2D materials. That's an example of some of the holes that we can drill, just 50 nanometers in diameter. We can build in these heaters, which we demonstrated. We can put graphene, single crystal graphene on wafer scale across these guys. We can do various different measurements and heating. And we're working with some folks at MIT who are actually building some of these sample holders in CMOS kind of foundries, where we can, do things like potentially put in optical detectors or apply local magnetic fields for actually controlling things at that scale. So we're kind of getting close to the point with, we've demonstrated that we can make little ribbons. We can decorate the edge of these guys. We can put dopants in the middle of these ribbons. Close to the point where we can maybe make devices, something like this, where we've got, we can have current flow through here, interacting with a single defect and gates across, so we can control the fields there. So I think we're getting close to being able to test these guys and really kind of span and look for what could be this potential replacement for the NV center in diamond, but in the 2D materials. And then finally, I won't do much on it other than to say that electron microscope is a pretty good microscope too. And so we're coming up with ways to actually do measurements in the microscope. So we can use the same kind of setup to use the electron beam to shine onto the whatever defect we make. It's kind of like a broadband electrical or optical excitation, or it behaves like that. And so you can get photons emitted from the surface, and you can study that. And so we can do optical spectroscopy with the electron beam, but at a much finer resolution, right? Atomic scale resolution, which is impossible with normal photons. And so with that, I'll say thank you. This is a slide I always put up at the end, which is, CMS is a user facility. Anyone can come and use our stuff if you fill out the proposal form. So if you want to get back in the lab, we can host you. And then finally, acknowledging all the hardworking folks that are helping to make that possible, and the folks that are funding it. There's a few papers. And just to conclude, to say that defects are awesome and graphene is liquid. So thank you.
Question?
Are there any practical applications yet of drilling those really small holes?
Yes, I mean, actually, a lot of that work came out originally from DNA sequencing ideas where they just needed a tiny pore to thread DNA through and potentially do measurements that way. That was one. There may be scalability is always a question, right? But there's potential to do work on catalysis, because a lot of these single atoms that you have embedded in the surface could be really great catalysts as well for certain materials or for certain processes. So there may be some options there as well. But quantum's nice because you don't need a lot of qubits to do something valuable. So yeah.
Curious, the gate you showed about a dozen slides back. Any idea of the radiation tolerance of such a device? Because my institution worked for Breakthrough Starshot.
Okay.
We worked for NASA. Spacecraft concept made of aerographene.
Mm-hmm.
Most everything, including the computation, is some form of carbon. Diamond can be a semiconductor.
Yeah, I mean, I would expect it to be robust. In fact, I gave a talk similar to this a while ago, and they were interested in, they put graphite inside of reactors because they're robust against, and they were interested in how do defects form. But yeah, I mean, obviously, graphene and graphite are really robust against radiation, so that might be an option. And in some cases, it heals itself, which is fabulous too, right?
Oh, wow. Like a spacecraft, autonomous spacecraft where the computation was healing. Yeah, that'd be big.
But I don't want to promise that. That's what
Well, our thing's like 50 years away at least.
All right.
Cool.
Since it's well known that you can stack graphene and twist it a degree and a half, that can become superconducting and so on. Does this imply that you're creating in the next higher dimension something equivalent to Bose-Einstein condensated two-packet on a global scale?
I don't know all the details on what you're asking. I will say though that there has been a debate as to what is the origins behind why you get superconductivity at that, and I think a lot of it has to do with the fact that when you do this twisting, you end up flattening the bands, at that junction. So, and it's that flattening that actually allows electrons to couple or to entangle in that band. So I believe that's kind of the best theory we have right now as to where that superconductivity might come from.
As you described everything, you're in the electromagnetic domain governing where all the atoms are with respect to each other, and now you're extending it one dimension higher. And it seems to me that you're looking at some properties of electromagnetism that are verging on the quantum things you're doing. It's a statistical thing, but maybe I'm wrong.
Yeah, no, I mean, I guess I'd say that this ability to make moire patterns is a wonderful opportunity, and we have been looking into different ideas too, where if we make these moire patterns, but we could dopants say on the nodes versus the anti-nodes, what kind of larger scale behavior could we get from that? And we don't even have to necessarily stack graphene on graphene. We put graphene on something like hexagonal boron nitride, which is an insulator, and get a lot of new properties that way as well.
Question? So,
It's just a practical question. How do you get one layer of graphene?
Yeah. Well, yeah, it's a painfully practical question. It's getting better though. A lot of it is, well, I'm sure the Nobel Prize in that area was they were using Scotch tape. They literally took a pencil, put Scotch tape on it, and then put it back down and say, hey, I got graphene, give me a Nobel Prize. But we're a little more sophisticated in that we can put 2D materials down, we can grow them, and we usually use a stamp that's a polymer type stamp that we can look through. And you can press it down, you can apply some heat to it. It helps adhere to the polymer, and then you can put it where you want. And so you can kind of watch it the whole time. To some extent, control its behavior. It's not easy by any means. There's other methods too. So for instance, we were able to we sent it out to a company that does it, but they could put graphene over an entire wafer. So they can grow graphene, they dissolve what it's on, and then they can kind of pick it up that way, kind of a wet transfer method. And then we've got folks at the lab who are growing graphene single crystal over square meters and other materials as well. So that's another really nice avenue.
What substrate do you put the carbon on?
For growth or?
Yeah, for growth.
Growth, I think it's typically copper. That's what I've seen mostly. But they're always testing different substrates as well to see what might work best.
You match the lattice.
I'm not sure if it's as much lattice as some other property that allows it to sort of hover and do its thing without really interfering with what's happening below.
Let's get back to the scalability question. Is a scanning probe technique realistic for a wafer size fab? Or are these sort of research level oddities?
Yeah, I mean, so two sort of answers to that is that, when we think about scalability in terms of classical, computation, you need billions and trillions of transistors. And so it needs to be really scalable. In quantum, like I said, 50 or 60 good qubits will get you where you want to go. So how scalable do you really need to be if you end up making a good device? And so it might not need to be that scalable. There is electron, e-beam fab set up, and so there's e-beam writers. That's not exactly what Intel would do, but you can still do quite a bit with electron beams in a normal fab setting. As of right now, we don't even know what the defect is that is the perfect defect, and so this is the setup that we want to do it. Well, if we find that perfect defect, maybe there's other synthesis methods that are more scalable that we can apply.
All the while you were showing these growth of these defects on graphene, I was thinking about Albini's experiment with the recrystallization of the silicon. Do you ever see any rehybridization of the graphene to sp3, the diamond form? That is two-dimensional, three-dimensional growth.
I don't think we've ever really seen that. I think it's
why?
just, I imagine it's just, it's hard to make diamond, and I'm sure it just prefers to be graphene, every day of the week.
It looks pretty stable.
Yeah, once you get it there, I guess, but I don't know. It takes heat.
Well,
time.
you're really moving. I mean, you had some of these odd defects, 7 atoms in a ring and so forth.
Yeah, maybe.
Another question?
Trying to understand how these things work. If you're trying to drag a given atom across the surface, do you have to tune the electron beam for that atom?
No,
Or generally?
Yeah, for the e-beam, we're basically making a hole that it can go into. And basically we evaporate atoms onto the surface that can run around, and at the right temperature, they'll kind of skate around.
You sort of wait for them to arrive.
Yeah.
You're not dragging them down.
No.
Gotcha. Okay.
There may be, e-beam is, it's at 200 kiloelectron volts. So it's got a pretty big field around it. So if that atom has some charge on it, it'll probably be attracted to that. Yeah. So we have that worked to our advantage, I guess.
One last question.
A couple months ago, we had a speaker who I thought I walked away thinking that he said there were quantum computers, a few of them in the world today. After hearing you,
no, they're definitely there. They're just, it's a few qubits and they work, but it's hard to do any long-term computation because the states dissolve so quickly, right?
what does the physical qubit look like?
And typically any of the ones that you might hear about in the news, it's these microwave resonators So they make a microwave resonator using kind of standard nanofab. Well, better than standard, but kind of using what Intel might use to pattern things.
AI exists without quantum computing.
Yeah. I mean, true. I don't know. What do you mean by true AI?
Well, I mean, the AI we hear about today seems to me like just, super special algorithms or software that takes a lot of data, snips it, sorts it, and answers the question, I guess.
Yeah. Well, no, I don't know if there's anything yet that we would know how to, make a true thinking, solving machine. But I don't know. The reasoning models are getting better and better. It's a little frightening. I follow that really closely.
Okay, one last question.
Back to the beginning of your presentation. I'd like you to define perfection. If I understood you correct, to make a qubit, two objects that must be identical.
That helps. Yeah.
So it's easier to make small things identical than big ones.
Yep.
So what's the limit right now, practical limit on how big you can make two identical objects? Truly identical.
Really identical. Yeah. I mean, to me, that's a few atoms, right?
Just a few atoms.
That would be my guess. Yeah.
Yeah.
I mean, nanotubes you can get pretty identical over extended distances, perhaps, but even that's complex as well.
Okay, thank you, Stephen.
So while you're sitting in section head meetings, you can look at that and think about your experience here. Thank you. Thank you.